This video will introduce you to the world of semiconductors. You will learn about the N materials and P materials. You will see how they are formed and how they function in solid-state devices. You will also learn about the depletion region in a semiconductor device, and you will see that by controlling the depletion region, you can control the device. Next, you will study many of the more common solid-state devices to gain a better understanding of semiconductor theory. You will see how these devices actually work. You're watching a listing of some of those devices to be covered in this video. Finally, you will see how many of today's integrated circuits are manufactured using a technique called monolithic fabrication. To gain a better understanding of semiconductor theory, we must first examine the atom. Here we see a silicon atom. As you may have noticed, the outermost ring of electrons are contained in an electrostatic force called the valence shell. In a pure silicon atom, the valence shell will contain only 4 electrons. The most electrons which may exist in the valence shell are 8. The closer the electrons are to the nucleus, the stronger the forces are that bond the two together. Therefore, each shell of electrons will have an associated energy level that will represent the amount of energy required to remove an electron from the shell. Since the electrons in the valence shell are the furthest from the nucleus, they will require the least amount of energy to become displaced from the atom. When atoms are combined to form a solid material, the electrons in the valence shell of each atom will be influenced by the forces created from the neighboring atoms. As these atoms merge, energy levels are created within the atomic structure of the material. In any given material, there are 2 distinct energy bands in which the electrons may exist. These are the valence band and the conduction band. Separating these 2 energy bands is a third band in which electrons do not normally exist. This band is termed the forbidden gap. The electrons in the conducting band are those which have been displaced from the valence band. These electrons are easily moved within the material with only small amounts of energy being applied. The electrons contained in the valence band, on the other hand, will require a much larger amount of energy to become extracted from the valence band and forced into the conduction band. Depending upon the type of material which the combined atoms form, the forbidden gap may be large, small, or non-existent. The difference between insulators, conductors, and semiconductor materials will depend upon the size of the forbidden gap within the materials. To gain a better understanding of this, we will first examine insulator materials. As you may have noticed, the insulator has a large, wide forbidden gap. Therefore, it will require large amounts of energy to displace the electrons from the valence band. For this reason, insulating materials make very poor conductors. Conductors, on the other hand, have no forbidden gap at all. The conduction and valence energy bands will actually overlap. Therefore, only small amounts of energy are required to move the valence electrons through the material. Conductors normally have very large numbers of electrons available for conduction. As you can see here, semiconductor materials have a much narrower forbidden gap than did the insulator materials just discussed. Therefore, the semiconductor material will require much less energy to extract the electrons from the valence band. But in the same respect, the semiconductor material will require more energy to displace these electrons than would be required by conductor materials. As a rule of thumb, elements with 5 or more electrons in the valence shell are considered electrical insulators. Elements with 4 electrons in the valence shell are considered intrinsic semiconductor material. And elements with 3 or less electrons in the valence shell are considered conductors. Silicon and germanium are the two most common semiconductor materials used in solid-state devices. The atoms contained in any solid material are held together by a force referred to as a bond. There are three kinds of atomic bonds. These are ionic, metallic, and covalent. Insulators are formed with ionic bonds. Insulators will contain both positive ions and negative ions, which create a strong electrostatic force of attraction between the atoms. It is this electrostatic force which bonds or holds the material together. The term ionic bond is used because the atoms are ionized. Metallic bonding occurs in materials which are used for conductors. As you learned earlier, conductors contain a large number of electrons which are available for conduction. As the electrons leave the valence ring of the atoms within the material, the atoms become positively charged and therefore become positive ions. A strong electrostatic force will exist between each atom and the many free electrons. It is this strong electrostatic force between the atoms and free electrons which forms the actual bonding of the material. Covalent bonding occurs in materials which are used for semiconductors. Covalent bonding holds the atoms much closer together than does the ionic or metallic bonds. Semiconductor materials contain both positive and negative ions. The positive ion will contain holes in which electrons could exist, while the negative ion contains extra electrons. Since the atoms are held closer together, the valence shell in each atom will share electrons with the neighboring atoms. This results in a strong covalent bonding action between the atoms. This sharing of electrons causes the atom to act as if each atom had 8 electrons in their valence shells. This in turn causes the material to act as an insulator. Silicon and germanium in their pure form are referred to as intrinsic materials. Before these materials can be used as a form of semiconductor material, they must have impurities added to them so the material can conduct an electric current. The process of adding impurities to the intrinsic material is referred to as doping. There are two classifications of impurities used for doping. These are trivalent and pentavalent. Trivalent elements will contain only 3 electrons in the valence shell, whereas pentavalent elements will contain 5 electrons in the valence shell. Common pentavalent impurities include such agents as arsenic, antimony, bismuth, and phosphorus. When a pentavalent impurity is added to the intrinsic material, it causes an extra electron to be generated, because when the covalent bond forms the two elements together, there can be only 8 electrons in the valence shell. Since the pentavalent impurities have 5 electrons and the intrinsic materials have 4 electrons, when the two are combined, there is an extra free electron produced. This free electron is termed a donor. Since the electron has a negative charge, the crystalline structure which was formed by the covalent bonding is called an N-type material. When a voltage is applied to the N-type material, the electrons will flow with only a small amount of energy being applied. Common trivalent impurities include such agents as aluminum, indium, gallium, and boron. Trivalent impurities contain only 3 electrons in the valence shell. This creates a vacancy or a hole when the crystalline structure is formed. Since this hole can accept an electron, it is called an acceptor. Intrinsic materials which are doped with trivalent impurities are referred to as p-type semiconductor materials. When a voltage is applied to a p-type semiconductor material, the holes will flow from the positive potential to the negative potential. This is known as hole flow and is only possible in p-type semiconductor materials. We will stop now for a short review of the material covered to this point. The maximum electrons which may exist in the valence shell of any atom is 8. The valence shell of the silicon and germanium atom will contain only 4 electrons. The closer the electrons are to the nucleus, the stronger the forces are that bond them together. Since the electrons in the valence shell are furthest from the nucleus, they require the least amount of energy to become displaced from the atom. Two distinct energy bands exist in any material. They are the valence band and the conduction band. A third band may exist which separates these energy bands. This band is termed the forbidden gap. Insulators, as you have seen, will have a wide forbidden gap. Conductors will have no forbidden gap at all. Their energy bands will actually overlap. Semiconductor materials, on the other hand, will contain a narrow forbidden gap. There are three kinds of atomic bonds: ionic, metallic, and covalent. Insulating materials are formed with ionic bonds. Conductors are formed with metallic bonds. And semiconductor materials are formed with covalent bonds. Pure silicon and germanium are referred to as intrinsic materials. Intrinsic materials must be doped with impurities to allow the material to conduct an electric current. The two basic types of impurities used for doping are trivalent and pentavalent. Trivalent impurities contain 3 electrons in their valence shell. Pentavalent impurities contain 5 electrons in their valence shell. Trivalent impurities are used to form p-type semiconductor materials. Pentavalent impurities are used to form n-type semiconductor materials. This concludes our first review. Next, we shall examine some of the more common single-junction semiconductor devices. A semiconductor diode will consist of both p-type and n-type semiconductor materials which are joined together. Here we see the schematic symbol of a general-purpose diode. As you may have noticed, the p material forms the anode and the n material forms the cathode. Where the two materials are joined is called the p-n junction. When the p-n junction is formed, some of the donor electrons will drift across the junction into the p material, leaving positive ions in the n material. As the electrons drift into the p material, it creates a negative potential which repels any further drifting of the free electrons. The positive ions in the n material create a positive potential which will repel any drifting of the holes into the n material. This small area where the drifting of the electrons and holes have occurred will form a new area within the semiconductor material. This area is termed the depletion region. The depletion region will have an equal number of positive ions on one side and negative ions on the other side. The depletion region forms a barrier which must be overcome before current can flow through the semiconductor device. For silicon-type semiconductor devices, this barrier requires a voltage of 0.7 of 1 volt before current can flow. And for germanium-type semiconductor devices, this barrier requires a voltage of 0.3 of 1 volt. It is this depletion region which makes it possible to control the semiconductor device. Semiconductor materials have majority and minority charge carriers. The majority charge carrier in the p-type material is the hole, while the minority charge carrier is the electron. The majority charge carrier in the n-type material is the electron, and the minority charge carrier is the hole. When any semiconductor device is used in a circuit, it will have a wide range of voltages being applied to it. These voltages are referred to as bias voltages. The bias voltage will determine how the device will react in the circuit. When a negative bias voltage is applied to the p side of the semiconductor and a positive bias is applied to the n side of the device, it causes the majority charge carriers to move away from the p-n junction. This in turn causes the depletion region within the device to widen. When the depletion region widens sufficiently, it will cause the majority charge carriers to stop flowing. This is referred to as a reverse bias condition. As you will learn later in this program, there are certain semiconductor devices that are designed to operate in the reverse bias mode. Within any semiconductor device, there will be a reverse current flow made up of minority charge carriers. As you learned earlier, the minority charge carrier in the P material is the electron, and the minority charge carrier in the N material is the hole. This reverse current is usually very small. It is typically about 1 microampere for silicon-type devices and approximately 10 microampere for the germanium-type devices. These values are based on a room temperature condition of 70 degrees Fahrenheit. There is, however, a limit to the amount of reverse current which may be applied to the PN junction. This limit is termed the reverse breakdown voltage. This voltage may range from a few volts to several thousand volts. When the reverse breakdown voltage is reached, the reverse current will increase at a rapid rate, which usually results in the device being destroyed. When a positive bias is applied to the P material and a negative bias is applied to the N material of the semiconductor device, it causes the majority charge carriers to flow toward the PN junction. This is referred to as a forward biased PN junction. If enough bias voltage is applied to the device, it will cause the depletion region to disappear and allow current to flow through the device. The negative bias on the N material will attract the holes in the P material and at the same time repel the electrons toward the PN junction. In the same respect, the positive bias on the P material will repel the holes toward the PN junction and attract the free electrons toward the positive bias. As the temperature is increased in a semiconductor material, both the electrons and holes will flow more easily through the material. This is due to the thermal agitation of the atoms, which increases the conductivity of the material. As the temperature increases, so will the forward and reverse current flow through the PN junction. Germanium devices are more sensitive to temperature changes than our silicon devices. The reverse current for both devices will be about double for every 10 degrees Fahrenheit increase in temperature. Since the current flows through a semiconductor increases as the temperature increases, it is said to have a negative temperature coefficient. The negative temperature coefficient will usually have a destructive effect on the semiconductor device. As the semiconductor passes current, it generates heat due to the electrons colliding with one another during the normal current flow. The greater the current flow, the more the electrons are agitated. This in turn creates more heat, which causes the device to further increase the conductivity of the material. This will continue until the maximum forward or reverse current rating is exceeded. When the maximum current rating is exceeded, it usually destroys the device. This phenomenon is referred to as thermal runaway. Transistors are more susceptible to this effect than our diodes. Now that you have an understanding of how the PN junction works, we will examine some of the more common special purpose diodes which you will encounter as a technician. You have already seen that when an ordinary general purpose diode is reverse biased, it will have a very small reverse current flow, which is made up of minority charge carriers. If this reverse bias voltage is increased sufficiently, the PN junction will break down and a large reverse current will flow. This usually destroys the device. However, there is a special purpose diode that is designed to operate in the reverse bias mode. This diode is referred to as a Zener diode. The Zener diode is designed to operate at a specific breakdown voltage when reverse biased. This breakdown voltage is called the Zener breakdown or avalanche breakdown voltage. When the reverse bias voltage of the Zener is reached, the diode will break down and a very heavy reverse current will flow through the device. If this reverse current flow is not restricted by a resistor or some similar device, the Zener would be destroyed by the excessive current. Therefore, when Zener diodes are operated in the reverse bias mode, there must be a current limiting device in series with the Zener to keep it from self-destructing. The current limiting device is usually a resistor. The value of the resistor is chosen so that the Zener will operate between its threshold current and the maximum Zener current. Once the Zener avalanche is on, the voltage drop across the Zener will not change. Even if more current is passed through the device, this makes the Zener diode an excellent voltage regulating device. When the reverse bias is reduced below the avalanche